Well, Geraint, it's that time of year again. It's Nobel Prize winning season. Did you actually watch it live? I was watching it live.
I did watch it live, and I must admit I was quite surprised. So, of course, I mean, when we talk about the Nobel Prize, we only really care about the Nobel Prize in physics, right? There's Nobel Prizes in something else, but
yeah, some other stuff, peace
yeah.
or whatever.
Yeah.
So yeah, I was watching it live, and it was really interesting to see which one came up this year. So in slightly controversial circumstances, astronomy/astrophysics has now got it 2 years in a row. So who won it?
Yes, well, so we should mention that often there seems to be a bit of a cyclical nature to the Nobel Prize, and it would be something like astronomical, then something applied and experimental, then maybe something else, But yeah, astronomy 2 years in a row. And in fact, I think a number of people were probably shocked because the three winners, Nobel Prize can only go to three people. One of them was Roger Penrose at the University of Oxford, who is a mathematician. And the other two were Reinhard Genzel, who is he's in Germany at the Max Planck Institute in Garching, and Andrea, who I believe is at UCLA. And they shared the other half of the prize. And the three of them actually work on, the Nobel Prize was awarded for a theme. So they haven't worked together on a particular project, but they've worked on a particular theme. And this theme this year was black holes. So it's a Nobel Prize for black holes.
All right, so let's break it down. What did Penrose do?
So Penrose is a very interesting character. He's very, very well known amongst the physicists and the mathematicians because he definitely thinks in a way I think a lot of us wish we could think in. And he's got this big, thick book, The Road to Reality, which is all the mathematics you need to understand modern physics.
It might be behind me somewhere.
Oh yeah, it is a slog of a book to get through. It's on my list to get back into.
It's somewhere. It might be at work.
Okay. So one of the things that Penrose has looked at over the years is this question of black holes. And we know that black holes originated with, firstly, Einstein's general theory of relativity in 1915. Then in 1916, the first analytic solutions. The first time somebody could write down some equations that solved the Einstein field equations, and that was Karl Schwarzschild, who was he was in the trenches in World War I on the Eastern Front facing the Russians. So it wasn't even the not so bad trenches on the Western Front, it was the Eastern Front. And he asked himself the question of, what does the space-time structure look like outside of a spherical mass distribution? So, you can take Newton's equation, you can work out what the force of gravity looks like outside of something like the Earth. But how do we portray that in Einstein's picture, which talks about curved space-time? And so he solved those equations, and what he found is that if you take all the mass and it's smaller than a certain size, then the mass basically has to, will collapse down, form a point, and you end up with these things we now call black holes, which didn't get their name until like the 1960s. And they were a theoretical curiosity, but one of the big problems that people had was, how do you form a black hole, right? So what you've got is, we now know the picture is that you take a big star, you let it evolve to the end of its life, it forms an iron core, so it can no longer produce energy. Gravity wins, star collapses, smash down on the core, crush the core, and that crushing basically forms a black hole. But the problem is that there was a lot of mystery about how matter can collapse into a black hole, right? Schwarzschild's solution was this beautiful spherical mass distribution, which you can, and his was not a dynamical solution; it was a static solution. So if you've got a black hole, you can describe it with the mathematics of Schwarzschild. But Schwarzschild doesn't tell you how you get the mass to collapse.
Right.
And of course, Einstein struggled with this entire concept throughout his life. He never really understood how mass could cross the event horizon, this particular radius beyond which you go into that radius, everything collapses down.
So one of the problems, as I'm sure you're uncovering at the moment, you're teaching GR, general relativity, is we have the difference between what's really happening in space and time and what's happening in our coordinate system. So,
Yeah.
for example, if you put latitude and longitude down on the surface of the Earth and you follow your latitude and longitude, if you walk over the top of the North Pole, suddenly things will change very quickly because there's a spot there where you have one of these coordinates, you don't really have the other one.
Yeah.
But there's nothing special about that point particularly. It's just that's something weird that happens with your coordinates. So there's a lot of problems in the early days of general relativity around both black holes and actually gravitational waves as well. Is this a real thing, or is this just our coordinates doing something weird?
Absolutely. And in fact, you're right. I'm teaching general relativity at the moment. And I just went through this issue, right? That the solution was actually known in the early 1920s. Eddington wrote a paper where he solved some of these issues about what goes on at the event horizon. But he didn't realize that that's what he had done. And it wasn't until 1959 and Finkelstein basically rediscovered this coordinate system that Eddington had proposed that they realized that the event horizon is this one-way permeable membrane, right? One-way membrane, you can cross in, but you can't cross back out again. But this was 4 years after Einstein's death, right, in 1955. But the question that occupied Penrose was, what if your situation is not perfectly spherical? Your collapsing star is not going to be a perfectly spherical object. So what if it's not a perfect collapse? And he showed that essentially within some range of conditions that any old sort of collapse, once it gets beyond a certain point, is going to continue to collapse down and form a black hole.
Right.
So what you've got there is that this notion that you can form black holes in collapsing stars, which are messy objects, as long as a few of these conditions hold, the formation of a black hole is sort of like a generic outcome that you should expect. So that was his contribution. And that's, of course, not his only contribution. And he's known for a lot of other things. And of course, one of the ones which is always fascinating is his work on tiles, how you can you can tile a floor with non-repeating patterns. So again, that's the kind of mind that we're working with there, right?
So I should say one of the reasons why it wasn't clear beforehand was if you do the Newtonian thing, take a perfect Newtonian sphere and let it collapse, because everywhere collapses together, everything will arrive at the origin at the same time, and so all the mass will be at one point, and so you'll have an infinite density, and so you won't, you'll get a singularity in Newtonian mechanics, except that you have to have an absolutely totally perfect sphere for that to work. Any little adjustment, any little difference, the tiniest little difference in the 1/1,000,000th decimal place, things don't quite get to the center at the same time, and the density is finite rather than infinite, and so you don't get a singularity. And so it wasn't clear at all whether the weirdness that happened in the Schwarzschild metric was just a result of this perfect spherical symmetry that had been assumed, or whether it was really there robustly. So Penrose showing that it was definitely there under very general circumstances was a major breakthrough.
Yep, absolutely. So that was Penrose. So that was theory in mathematics. And it's kind of rare to get that kind of Nobel Prize, right?
Yeah, someone pointed out this is the first Nobel Prize awarded for theoretical work on gravity ever.
Absolutely, because Einstein
didn't even get it. Yeah.
Yep, he got his for his contributions to science, including the photoelectric effect, which is, that I think that was the actual citation.
All right.
But of course, it included special relativity, etc. He got his Nobel Prize, I think, in 1921. And, general relativity, it was only in 1919 that Eddington did his experiment that showed the deflection of light. General relativity was still a bit new, a little bit out there. So that's one half of the prize.
Right.
Other half of the prize goes to Ghez and Genzel. And their focus was what's going on in the middle of our galaxy. So they weren't working together either, independent groups. And Andrea Ghez has for a long time been working on a project where you get the sharpest images you can of the very center of the Milky Way. Now, from a lot of arguments, we thought that point in the middle of our galaxy should host a black hole with a mass, I think it's 4 million times the mass of the sun.
Give or take.
Give or take. But it's not accreting matter like lots of black holes we see out there in the universe, right? Mm-hmm. What we have is this thing is sitting there and there's not gas swirling in, and we can see black holes in a distant universe because of the way they influence gas. But what is there a black hole in the center of our Milky Way? So what Ghez has been doing and Genzel have been basically trying to do this high resolution imaging of what's going on in the very center of the galaxy and tracing the paths of stars as they move around. So, these stars are moving on elliptical orbits, or we'll come back to that. They're on roughly elliptical orbits. Mm-hmm. And some of them are swinging very close to absolute nothingness and then doing a very sharp turn and flying back out again. And what these results have been able to show is that these stars, which are moving at tens of thousands of kilometers per second, mm-hmm. are orbiting this nothingness. And the only thing we have in our theories that can be that small and that massive must be a black hole.
Yeah.
And in fact, we've gone one stage further. What we're also able to show is that as these stars get very close to the black hole, you've got to use general relativity to describe their motion.
Yeah.
Newtonian gravity just doesn't cut it anymore. So
it's really nice.
It is a spectacular result.
We'll stop here to show. We've shown it here before, but there's that video that I show basically anytime I get an excuse at a public talk of watching the center of our galaxy since 1995, and like you just described, don't see anything at the center, but every now and then a star, an enormous amount of matter moving incredibly fast just makes a complete U-turn in a very short amount of time, in a couple of months.
Yeah. And in fact, just a bit of a personal story. I met Andrea Ghez when she must have been a young postdoc because she visited the IOA in Cambridge. I can't remember how long she was there for, but I think that was the starting point of this project, right?
Nice.
That goes out for 25 years to today. I also have some history with Reinhard Genzel, which involved a football game and a rough tackle, but that's not really for this discussion here.
Yeah, we all need a beer or two before that story comes out. I think I have actually heard that one. Yeah. She visited the University of Sydney. You're still there while I was there, and gave a talk. And I got the chance to ask her, given the population of stars flying around, how long do we have to wait on average, maybe, until we really see something totally get ripped apart, like fall in, all the business? We haven't quite seen that yet, but the answer was sort of roughly, it might be a 10-year timescale, it might be a 100-year timescale. It's a bit hard to tell, given that we've been watching it for 25 years now. Hopefully on one of these turns around, something just wham hits it. Yeah. That would be amazing.
I mean, there have been some interesting flare-ups, right? They do think that some things like comets might have been pulled apart, and that there was a gas cloud that was orbiting that was being shredded as well. So, we know that it's gravitationally, it's a violent place at that very central point. But the fact now that we know it's a violent place, but it's relativistically violent, not just Newtonianly violent, I think is very important.
Yeah. Let me throw up something. Hawking was sort of there. Stephen Hawking was famous for this sort of work as well. Now, when Penrose published the paper that really got him the Nobel Prize on this in 1965, I believe, at that point, Hawking is still a PhD student, but he's working on similar things. I think he finishes his PhD the next year in 1966, and Penrose is one of his examiners. And they obviously hit it off and start doing more work on this topic there. This topic then leads to singularity theorems more generally, the cosmological singularity theorems, the singularity, the beginning of the universe, all that sort of wonderful stuff. Should Hawking, I mean, they don't give it posthumously, and you can't give it to 4 people. So, but should Hawking have gotten a piece of this if that had been possible?
Well, it's an interesting question because up until this year, I guess I would have said that Penrose wouldn't have gotten it because I didn't think the Nobel recognized this kind of theory.
Hmm.
Right? As you said, it's not really something on their books. It is. It's quite esoteric. It's quite out there. It's quite difficult to understand.
It's very mathematical.
Very,
It's
very.
not just honors year general relativity mathematical. It's beyond that mathematical. It's very serious stuff.
Yeah. I would have guessed if Hawking was still alive, I think he would have been in the running if they were going to give this to Penrose, that Hawking would be involved as well. But then you've got 4, and you can only give the Nobel Prize to 3 people.
Yeah.
So it is a. I have mixed feelings about the Nobel Prize. I feel it is a prize for the early 1900s, not the early 2000s.
Yeah.
And it doesn't really reflect the way that science is done. So, look, Penrose, fair enough, paper and pen theorist. But Genzel and Ghez are heads of big groups using big telescopes. And of course, the credit does sort of rain down on the groups, but only 3 individuals get their name on the prize. So, they will be remembered. And I'm sure there will be some people who are already a little bit grumpy. I've seen some emails flowing around about people being a bit grumpy about, well, the technology and the insights that founded the instrumentation that these discoveries are made on.
So, and let's talk about that for a second, because, I mean, Ghez, well, both of them, they're using what's called adaptive optics, which is really, really amazing technology when you think about it. As light, suppose, a burst of light comes down and it's coming through the atmosphere, because the atmosphere isn't uniform, that nice, wave front of light gets a bit distorted. And what adaptive optics does very generally is to keep an eye on something nearby and to try and trace the distortion of light through the atmosphere, and then deform the mirror of the telescope to sort of counteract that, so you get your nice smooth light coming through again. And you need that so you don't just see, when you look at the center of the galaxy, just a blur, so you actually can pick out those individual stars. So, yeah, you're quite right. That is.
So, and of course, some of these they actually have their own source that they monitor. They shoot a laser up through the atmosphere, and they monitor the laser, and they change the often the secondary mirror to sort of, as you say, cancel out the distortion. But also interferometry comes into this as well, right? So to get the highest resolution images, you've got to go beyond just taking a picture. So this is gravity, I think, is the ESO instrument. It's a cast of thousands, but the prize rewards individuals. Unless it's the Peace Prize, and then you can award a group, right? So like the World Hunger group that got the Peace Prize this year.
All right, so there's 2 ways to solve this, I think. Either you only ever give it to theorists who are working by themselves. I'm happy with that. Or, maybe the Nobel Prize should reconsider whether they can give it to groups, because other prizes do that. I mean,
absolutely, other prizes do, but the Nobel Prize is.
Oh, you can't change it.
Yeah, it's written in the statutes. They have changed the statutes over the years, but it's in the spirit of what Alfred Nobel wrote down, and et cetera, et cetera.
Well, let me put up that video again, because it's the best. Yeah, but just watch this a few times.
But we should finish on one interesting little point.
Oh, okay, good.
So Roger Penrose has thought of lots of things. But in relation to our book, the Cosmic Revolutionary's Handbook, he has his own cosmological ideas about the universe, about how the universe basically is a cyclical universe that gets reborn over and over again, etc. And it is basically supported by him and possibly 1 or 2 others, and everybody else says that this is basically ruled out by observations. Just because a Nobel Prize winner says something doesn't mean that it's necessarily true.
Yeah, so he's put out these ideas that if you look hard enough at the cosmic microwave background and see this video for the cosmic microwave background, we can see not just complete randomness, but circles, which are, according to his theory, remnants of I think supernovae or black hole explosions that went off in a previous universe or something like that. And time and again, he publishes something, and someone who actually works with this cosmic microwave background says, no, that's not good data analysis. Here's good data analysis. No, your circles aren't there. And we've been around that loop 3 or 4 times by now.
Absolutely.
Oh, well, all right. And now we're going to show that video again, and you're going to all watch it and enjoy it.